Hello world, here's Jorge and let's continue learning about object detection in PyTorch. In the last video we defined a function called loadData, which essentially first deserialized our file sciencedata.pth, and then based on the chosen object class, a list of class labels was defined. And then in the second part, what happened was essentially the filtering of the data. And first of all, a list of labels was defined. This list contained all the labels for the boxes. Yeah? And something that is important to stress is the following. These labels correspond to the bounding boxes only and not to the entire images. Okay, because you might be used to be working with supervised image classification problems where your labels in the trained data set, they correspond to the entire images. This is not the case in this problem. In this problem, I stress that these labels correspond to the bounding boxes only. Okay, then after that message, let's continue with the function. So after the labels, what we did was to define a list called cell. Okay, and here we stored all the indices that corresponded to the class labels that were actually selected, and with selected I mean that they correspond to the chosen object class. Okay, but there's no better way to understand how especially this second part of the function works than by going through an explicit example. Okay, so let's do that right now. So suppose that the list of the entire, say, so the whole list of labels is the following. Okay, labels. Just again, this is a very like dummy example so that we can understand how it goes. So let's just say that we have this list of labels for all our boxes. Okay, so in that case, then we would also need to have a meta label list. That meaning, what is the list that corresponds to the object class that has been chosen? So let's suppose that this meta labels list is the following. Is, say, for instance, 1 and 3. Okay, these are the classes, the class labels. So if that's the case, how would the cell, the corresponding cell list look like? Well, remember, cell is the list of indices that correspond to the class labels that have been chosen. So in this case, 1 and 3. So we just need to see, okay, so what are the indices that correspond to in the labels list that correspond to 1 and 3 values. So in this case, you see, this is the 0 index in the labels list, 1, so it would be actually 0, and then we have also 1 here again, so then we need to state here 2, and 3 is also appearing, so then we would have number 3. Okay, now it's more clear. Now let's go through the actual subkeys. Yeah, the filtering through the filtering explicitly. So let's do that, and remember that we the last videos we defined data. Okay, we defined data right here, which is remember the deserialized data. So using that, let's go through the filtering process explicitly. So we have, let's just focus on train. Again, for vol is completely analogous. So train, and let's start with boxes. Yeah. So right there. Remember, this is going to give us a series of 4D vectors. 4D vectors and say each box has a 4D vector associated to it. So let's just have a look at 5 boxes, like 5 4D vectors. Okay, yeah, it's totally fine because I didn't run the cell. So let's do that right now. Great. And let's see. Okay, you see we have these 5 values. Remember, each vector corresponds to 1 box. All right. Right now, imagine that we're going through the second part of the function. So what we need to do is to apply the selection. Apply the selection so that we just have the say boxes that have been selected, have been filtered. Okay. So how can we do that? Look at this. We have a tensor, and what we can do is to just say, okay, what happens if we just slice it with select? Okay, so just to have so that we can compare this print the previous operation. Okay, so and let's print also this one. This is just for the sake of comparison between the two, and let's just put here a simple space. Okay, great. So you see, well, see that the selected options for us are 0, 2, and 3. So 0 is the first vector, the first 4D vector, and as you can see, this has been selected as expected. Okay, then the number 2 is going to be the third index, so this one, and as you can see, here we have it. And finally, number 3, indeed, this is what we have, is this one right here. Great, makes sense. But look that above, we also included the columns. So it actually, what is happening is that the columns are selected all by default. Okay, so actually now that we have realized about this, we can just get rid of that. Okay, that's regarding the boxes. Let's continue now analyzing the different filtering criteria, and now let's move to the box images. Okay, let's move now there. And so what we need simply to do is just say, okay, so instead of boxes, we're going to have box images. Okay, let's see how this looks. Okay, so indeed we have different image paths, and what do we need to do here? Well, we need to filter just like we did before. And how can we do that? Well, this is a list of strings. So what we need to do is to look through that list, because a list is iterable, so we can look through it. So let's do that right now. So which is what we did above. So we can simply say, okay, instead of having directly the output, what we can do is just to define list comprehension. We can define list comprehension where we're going to loop through the so what we're going to have is, as an output, we're going to have all the selected image paths. And the loop is going to look as follows. So basically we're going to have index and in actually the list of cells, because we need to look through cell, yes. So indeed, this should give us the selected image paths. And as you can see, remember, cell, let's just print it out here to recall this. Okay, so it's 0, so 0 should appear. Indeed, it's here. Number 2 should be this one, so indeed appears here again. And 3 is this one right here, which is indeed showing up in here. So definitely makes sense what we are seeing, and definitely is helping to understand further. And what can we do next? So just follow the filtering, and now let's do box labels. Let's do box labels now. So box labels, train, and here labels. Okay. All right. So let's see how this looks. So remember, labels are just the numbers, indeed, associated to the bounding boxes. And how can we continue? So essentially, we need to apply the filtering criteria. So again, let's think about this. Well, this is a tensor. Okay, so the question actually I have is, can we loop through a tensor? So can we loop through, because we know we can loop through a list, but can we actually loop through a tensor? Well, let's try it out. So print, and we're going to follow the same logic that we did previously with box images. So essentially, we're going to have box labels, and we're going to actually define list comprehension. So list comprehension right here to get a list. And again, we're going to select the box labels that we are interested in. So for I in the list cell. Yeah, in the list cell. Okay, let's try this out. Let's try this out and see if it works. Okay, it worked. It worked. However, see that all the elements now are tensors by themselves. So now what we have is a list of tensors, but just of the labels. But the labels are not tensors. The labels are integers. Okay, so this is not 100% correct. So because these elements need to be integers. So what can we do to transform the tensor, a tensor, to a Python integer? So just as we saw in the previous videos, dot item. Okay, so if we dot item this, we should get a list. Yeah, exactly, a list of integers. Okay, but now what is the problem? The problem is that this is a list of integers, but is not a tensor of, basically we don't have a tensor that embeds a list of integers, which is what we want. We want something like that. We want a tensor that has a list of integers, right? We cannot change that format. So how can we achieve that? Okay, so well, because this is not what we want, but okay, we learned about say how structuring data. What we can do now is just say, okay, let's take this, exactly the same, and instead of basically instead of looping through it, what we can do is just say, okay, I just want you to give me the selected say labels straight away. So in that way, you see, we get a tensor that contains a list of integers, which is what we wanted, and which is what we originally set in our function. Okay, so nothing changes. And what else can we check? So we can check the box patches. The box patches, yes. So let's do that now. Box patches. And okay, so what we can do now is to just have just select some of them. Again, this is a lot of information explicitly say shown. So what we can do is just see the shape. We want to see the shape. Okay, so what we have is a 4D, and remember that 5 refer to the number of patches. And actually, let's have a little conversation about, let's talk a bit about these, what this number means. Okay, so this number indicates the number of patches, or in other words, the number of cropped images that we're having, or we have. Yeah, so this indicates that these say Tensor has 5 cropped images. In this case, 3 with 3 color channels, typically red, green, and blue, and this 64 as height and width. Okay, great. So now let's select these the desired or the filtered image patches or box patches. Okay, and how can we do that? So essentially what we can do is just directly as we saw in the last video, just indicate that we want the selected. Okay, this is going to give us directly the selected images. Okay, well, and why did it go from 5 till 3? Okay, remember, we have originally, okay, we had 3 indices stored in this cell list. Okay, this means that we have 3 say chosen class labels. Okay, so this is why we have 3, because there are 3 elements in cell. Okay, so it makes sense. Great. Now we understood further the function that we defined in the last video, this function load data. But now it's time to move on. So now what we can do is just, for the sake of this practical, stick to one of these, say, object classes. Okay, and let's just say let's go for the mandatory. Okay, let's just go for the mandatory. So let's now just call the function. Okay, because now what we're going to do, we're going to leverage the fact that we have this lab.py. This lab.py uploaded to Colab, basically. So we're going to use that fact. And how? So we just need to import this file. And also something that we can do now is to turn off the gradients. Okay, why should we do that? Well, the gradients are only used for training when you are updating your features. Okay, but here we're not training, we are pre-processing our data. Okay, so we don't need the gradients, hence we're gonna turn them off. Yeah, how? Well, we can just say torch.set grad enabled and false. Okay, in that way we turn off, or we basically are telling that we are not, so turn off gradients, or in other words, essentially no need to update gradients because we're not training. Okay, all right, so what else? Now what we can do is, okay, say the filtered data, yeah, is going to be the mandatory road signs. Okay, we chose that. So let's call the function, and we're going to say load data, and we're going to select the mandatory object class. Yeah. All right. And this will help us to visualize later on our cropped images, because actually that is the next step. Okay, we want now to visualize our filtered data. Okay, let's do that now. Yeah, so essentially we have filtered our data so that the resulting images are all mandatory road signs. This is exactly what we just said, yeah. But now what we want to do with the filter data is to, first of all, we want to rescale it. We want to rescale the images, okay? We're going to need to do that. And after, what we want to do is to plot the actual chosen data. So we want to showcase the data that was filtered. Yeah, and in this case we expect mandatory signs only because that is the object class that we chose. Okay, so we are going to define two functions. We are going to define two functions to end up visualizing our filter data. Okay, so what are these functions? So the first one is going to be IAM-SC, and this function, so this function is going to actually rescale. It's going to rescale, and with rescaling I mean that our data is going to be between 0 and 1. So all the data is going to be in that range, and then we're going to plot it. Okay, and actually we're going to implement in our function the possibility of turning the plotting off. Okay, well, we will see that later. So we want to plot an image. Okay, so after having obtained its numerical representation. So what I mean is that, of course, we always have images, right? And these images need to be turned into numbers because that's what computers understand. So that is why we need to turn those images into actually more precisely floats. Okay, then that's number one. Number two is going to be the function called so basically image array as scaling. Okay, and we'll see why this array is important to stress. Okay, while we define the function. So so this function, is going to plot an input tensor with dimension n c h w, which, remember, n meant the number of cropped images, c the color channels, h the height, and w the width. Yeah, and this input is going to then be transformed into basically representation that has the following shape. C, so channels, MH, and NW. Okay, well, we are familiarized with all these variables except for this m, right? So this m is just say a numerical factor that represents the number of rows of the final, say, representation. But don't worry, because we'll get there, so no hurries there. Okay, and something important to stress is the following, that this function, this imArraySc, is going to leverage the IMC's capability. Okay, so basically the IMC's capability to rescale tensors to the 0-1 range. Okay, great. But yeah, let's go step by step, and now let's focus on the image scaling function. Yeah, let's do that. The oops. Yeah. Okay. Well, something that is important to also include here is that the function takes as an input tensors of the shape 3, height and width, or 1, height and width. So this means that if our input tensor is not having either 1 color channel or 3 color channels, it's just going to yield an error. Okay, and that's important to highlight. Well, what else? So now we are going to go straight to basically understanding how to define this function. Yeah, so let's start by just giving say a real world example of say a tensor that we want to say pre-process. Okay, so imagine that we are given a tensor, yeah, with the following shape. Okay, so let's say we have an image that has, yeah, so this numerical representation. Essentially, we're gonna have, for instance, this is just a random example. Okay, say we have minus 10, then we have 20, then we have this. Okay, all floats, yes. So we have this tensor, okay? Just to, well, no, let's see this, and then let's just, of course, the shape. Of course, is a 2 by 2, yeah. But okay, what is the say? Well, we see some issues here. Okay, the first issue we see here is that this number is negative. Yeah. Well, we cannot have pixels that are negative. These basically don't have any meaning, right? So this needs to be transformed. This needs to be transformed to a positive number or a 0. Yeah. And the second issue we see here is that there's no 0. Remember, we need to have our data rescaled. Yeah, this means that our floats need to be between 0 and 1. Of course, as our tensor has not been preprocessed yet, this is not the case. So we need to also tackle that issue. Yeah. So how can we start, say, rescaling our tensor? Yeah. So what we can do is to actually take the minimum of the tensor, take the minimum value of the tensor, and then subtract the original tensor to this minimal value. Okay. Why are we doing this? Well, if we do that, we are going to first of all get a zero within our tensor, which is crucial to, say, get our tensor rescaled. And second of all, we're also going to get rid of the negative value, which doesn't make any sense, say, when it comes to image representation. Yeah. So let's do that, and let's just explicitly say this. We need to rescale the image in this case. Yeah. So how do we proceed? So let's rewrite image in the following way. We're going to have the original minus the minimum value of the original tensor. Yep. So let's see how the output looks like. Fantastic. So you see, first of all, we get 0, and also we get rid of the negative value. Yeah. And as you can see, this the minimal value, which was a minus 10, yeah, was subtracted to the original say tensor. Of course, minus in front of a minus is plus. That's why there's a notation here. But as you can see, all the values change. Great. That's the first step. The second step is to actually we need to normalize the tensor. Yeah, that meaning needs to be between 0 and 1. Right now, that's not the case. Yeah. So how can we do that? So what we can do is to use, say, Python's capabilities, and Python has the method mul. Yeah, so that it allows us to multiply by a scalar, and this scalar needs to be basically the inverse of the maximum value of the original tensor. Oops, image max. Yeah, great. So this should yield, indeed, you see, we have values between 0 and 1, all of them. Okay, great. This is already normalized. Okay, so some of the issues have been solved, but remember, we said that our input tensors, they need to be not basically either 3 by h by w or 1 by h by w. So in this like at this stage, we just have 2 by 2. So we need to include say this color channel. Okay, so it's your choice. It's your choice to either go for 1 or 3. Yeah. So yeah, let's just go for 1. Okay. And how can we do this? Well, we can unsqueeze our tensor. Yeah. So remember, so unsqueezing. Yeah. This is just going to add a dimension at the beginning of the at the beginning, because we choose to do so. So what we can do, let's see docstring here, you see it's dimension, and this is going to allow you to decide where to place your extra dimension. Yeah, so let's place it in the first position. Yeah, and yeah, if we do that, we're gonna get an extra dimension. You see, how do we know based on the output that we have an extra dimension? You see, we have 2 brackets here. That's 2D. Now we have 3D. Yeah. Okay, but let's say we want to see explicitly these extra dimension, right? So how can we do that? So just shape to compare. You see, of course, you have a 2 by 2. But if you want to see it here, so just dot it but with shape. Indeed, you see. Fantastic. We have 1 in the first position. Great. All right. Now we already have the format for our input tensor that is going to say allow us to continue with our function definition. Okay, so what can we do next? How can we proceed, say? What we can do now is to say expand our tensor. And what do I mean by that? Well, what we need to do now is to actually say work out a bit more these tensor so that we can plot it, because remember, we want to plot our tensor. Yeah, and we're going to use Matplotlib. Okay, so Matplotlib has certain conditions to say be able to plot the tensor that we're working with. So what we need to do is the following. We need to first of all, we're gonna take the input image. Yeah. So what I mean is that we're gonna take the we're gonna take actually the original. We're gonna take these 2 elements, the height and width for now, just that. And how do we do that? So just we're gonna say okay. Yeah, I wonder if now, if I do image, what has been stored? You see, it has not been stored. It has not been stored because we have not, say, stored our unsqueezed tensor in a variable. We have not done that. So we actually need to do that. Yeah. And yeah, so let's do that. Let's do that first, like before proceeding. Yeah. So what we can do is the following. Let's do it here. So let's update it with just image. Let's call it the same way. So image dot and the unsqueeze. Okay. Okay, just the same thing. And yeah, and great. And in that way, we're gonna get the image with the unsqueezed. Now, oops, wait a second, because now I see 4 dimensions. Exactly, watch out, because we have a problem here now. So we need to actually unsqueeze. We need to actually squeeze now. Squeeze this. And see. Now it's 3D. And that's the image shape. Okay, now it's correct. Great. So now we are going to proceed. We're going to proceed with the actual definition of the function, because we already have all the information we need to proceed for just straight away with the definition of the function. So let's do that. So let's define the function. Now that we have a bit on, we have understood how to construct it. Well, so let's do that. So let's put it. I said 2.2 here. So let me, 2.2.2 explicitly write down. Yeah. No, it doesn't matter. I can definitely write it down straight away. Okay, so let's do define and IMSC. And what are going to be our arguments here? So our arguments are going to be the following. Well, the docstring already shows you, I guess, because it has been uploaded to Google Colab already. I wonder that. I'm not sure actually. But anyways, let's define it right now. Image is going to be our input tensor, yeah, and that it's essential to have it defined. Then we can do the following. We can do say, okay, the quiet mode, and we're gonna set it by default as false because we want to get the plot out of the function. Okay, once we call it, and afterwards, what we can do is to just add some arguments, okay, and these are optional, and these arguments are going to be essentially useful to then add, say, more features to our plots, okay, but for now, let's not do anything with them, okay. Okay, now what we're gonna do is first to define variable called handle. Okay, why do we need this variable? Because once we have written the whole function, we're gonna return. First of all, we're gonna return the actual image. Okay, we're gonna return it, and we're also going to return the plot. Okay, so we're gonna, this image, remember, has been already rescaled once goes through the actual function, yeah, and then we're gonna return handle, which is going to basically allow us to get as an output the plot, yeah. But remember, there are two options. Either we have the quiet mode turned off, as is right now, or can be turned on. Yeah. What happens if it's essentially quiet? Okay, if it's true, yeah. If that's the case, well, we're gonna have no plot return. So we need to set this to none. Okay, because in that case, we're gonna return none. Yeah, great. Then what's next? Well, remember, we are preprocessing. So there's no need to have our gradients basically being updated. So we're gonna say we're gonna turn off our gradients, okay? And how do we do that? Well, we can apply the inference mode method. So torch dot inference mode method. Okay, this is going to, well, let's actually search it, torch.inference mode. Okay, so this is going to allow us to disable, yeah, the say prediction mode. And also remember, there's another class that is able to turn it off. It's called a no-grad, torch no-grad. And but I've basically read that in the literature that it is actually recommended to use inference mode instead of no-grad. Okay. Okay, let's continue. We have turned off our gradients, and now let's just apply what we learned above to normalize our data. Remember, we had to first subtract the minimum value, so let's do that. So m is equal to itself minus the minimum value of the tensor. Okay, then that's the first step, but then we also needed to normalize it, yeah, and we did that using the mul method in Python to multiply the already say modified tensor with the scaling factor, yeah, which was essentially 1 over maximum. Yeah, exactly. So that's how we get it. What can we do next? Well, remember, all this is in the case that we have quiet mode turned on. But what if the quiet mode say, well, sorry, if it's actually let me think. We have by default the quiet false, so the quiet mode turned to be false. Okay, so if it's not quiet, okay, if it's, exactly. So if we have the mode to be not quiet, it's not quiet, we're gonna have the following. We're gonna have in that case we're gonna have the plot. We're gonna have the plot, exactly, because this is for the case where essentially when the plot is quiet. Indeed. Okay, so if it's not quiet, then we need to plot. But before plotting, we need to modify our input tensor so that it can be plotted with matplotlib. So how can we, so what kind of modifications we need to apply to our input tensor so that it can be applied, so that matplotlib can be applied? So first of all, we need to have we need to expand our input tensor. What do I mean by that? So we need to actually get the input tensor. So what we need to do is the following. Okay, we need to get our, let me think. How is this working? So remember, we had, after unsqueezing, we had these object here, with color channels first, then height and width. So what we need to do now is to just select these two, the height and width, out of the tensor. How do we do that? Well, what we need to do is to say, okay, we're going to take the shape, and specifically we're going to take the second and third element, or in this case, so we start from index 1 and the rest. Yeah, that makes sense. And now what we need to do is to actually expand. We need to expand these object here. Yeah, and how can we expand it? Well, what we can do now is to use the star operator to unpack the argument out of a list or a tuple. Okay, it can work either on a list or a tuple. Yeah. Well, in this case, what do we have? Yeah. So we have, as you can see, we have a list here. Yeah. So this should then work out the star operator. So let's apply it here. It's in here. So star operator to expand, and matplotlib is going to actually only work with 3 as color channel. Okay, so we need to put here 3, and now we need to expand. We need to expand our original tensor. Okay, all right, so we have this expansion right there. So all right, once we have that, can we just define a variable and then plot it? Okay, so let's call this map, because this is actually going to be our background. This is going to be our background plus, let's call it like that, to then achieve the final result, which aims to be essentially what we aim to have is just like a frame, to have a frame containing all the, in this case, remember, mandatory road signs. Okay, but before getting the final output, we need to create the background, and this step right here, this map, is the background that I'm referring to. Okay, but this is not enough. Why? Because remember, our input tensor, you see, is either a 3HW or a 1HW. Yeah. But with matplotlib, we need to have the color channels last rather than color channels first, because PyTorch works with color channels first. Okay, but matplotlib does not. Matplotlib works with color channels last. Okay, so we need to swap that. We need to swap the order. So how can we do that? So essentially, we need to permute. Yeah, so we're going to permute our tensor, and remember, we want now the color channels to be last. So originally is first. So now originally it was index 0, but now index 0 needs to be last. Yeah, so like that. And what happens is that the second index now is placed in the first position. So this means that 1 is going to be here and 2 is going to be here. Great. Okay, so we already have this. But what is the problem? What is the problem? The problem is that as we have it right now, yeah, we don't have an array. All right. Remember, matplotlib only works with arrays. Yeah. So to turn our object here, so to transform it to an array, we just need to call here the numpy. Yeah, we need to call here numpy to convert our object to an array, so that can be plotted with matplotlib. Okay, great. So now it should be okay. And now let's continue. And what we're gonna do is to actually say plot it. Yeah. And remember, handle is a variable that is going to output the plot. So handle is going to be equal to the plot. Yeah. And in this case, we're going to use imshow. So here, and it's going to be map, and well, and the different arguments that remember that I told you, basically that are used to update or upgrade per se our plot. Okay. Great. So what can we do next? What we can do now is to basically extract the the axis. So the labels that are set to the axis, let's extract them, because basically we are not going to have any labels on our axis in the final plot, because we just want to portray the frame containing all the mandatory signs without labels on the axis. So let's get rid of that. And to do that, let's start doing the following. So axis GCA. Okay. And basically, why are we using this GCA method? Because we want to modify the axis in a way that we are not going to output labels associated to these axes. Okay. All right. So we're gonna say, okay. First of all, how are we going to modify this axis? So first of all, we're gonna turn them off. And then we are going to essentially, set them empty by just stating the following. So this is going to turn, so this method is going to get rid of the label in the x-axis, and the same is going to be done for the y-axis. Yeah. Great. So that's it. That is our function. And yeah, let's try it out. So remember, this function is going to work only with the tensors that have as an input say either 1 color channel or 3. Yeah. So having that in mind, let's proceed. So let's just have a random tensor defined, and we're going to have torch dot random. Okay, just a random tensor, and doc string. Okay, great. So we have a list, and let's just start with gray, just with 1 color channel, basically white and black. And just say we want 3 as height and 3 as width. Yeah. Yeah. So technically, with that, we can just call the function. Okay. So MSC random tensor. Okay. Great. You see, we have 3 by 3 plot, yeah, with a black and white, basically the gray color channel that we chose, yeah. And also, because this is the second output, this corresponds to handle. But remember, we also have the im output, which is the rescaled tensor. And something that can be useful is to actually visualize the original tensor so that we can compare. Yeah. So we can do is print, and it's random. So keep in mind that these values are going to change. Yeah. So tensor this is the original tensor. And let's put here, just for the sake of clarity, and here. Great. So you see, this is the original tensor, and you see how we have actually several negative values which don't make sense, yeah, for when we talk about pixels, and see how our transformation gets rid of, first of all, the negative values, and second of all, it actually rescales the values as we want. So you see that all values are between 0 and 1 is expected. Great. And here's the background that I was talking about, yeah. But let's just for fun see what happens if we put 3 and 2. Of course, this one going to change is the width. Okay, so what we expect is indeed, yeah, exactly. We have 3 rows, like our height correspond to our height, and 2 columns correspond to our width. Fantastic, fantastic. So and also for fun, let's just say a 3 here. Great. So we get 3. So we get a colored output, because now we are dealing with the say red, green, and blue color channels. Yeah. Well, yeah, that's been all for this video. I hope it was useful for you, and I am willing to see you very soon.